In this section, we're going to deal with two concepts. The first of these is how we deal with scientific notation, a special kind of notation that allows us to use very large and very small numbers. And secondly, how we deal with accuracy with these associated numbers, because it turns out we can never measure anything exactly. Let's first look at the scientific notation. When we look at a number, often these numbers are very, very large. Like, for example, we might have 300 million people in the United States. So it might be 346,000,000. And if we're looking at this large number, we represent this in a scientific method by representing it with a decimal point at this position and then multiply a power of 10 that will move the decimal point to the correct position. So we would write this as 3.46, and we really don't know what these digits are, so we omit those digits, implying those digits are really unknown and we don't have that accuracy. And we can write this as an exponent times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. So that would be a plus 8 or just an 8. Or we can write it as 3.46 times 10 to the 8th power. Now, this method is more common now with computers because with computers we can type this a lot faster than we can type this. And so this has become an accepted method of entering what is called scientific notation. The E should follow the 6 immediately and not have a space in between. The plus can be omitted or it cannot be omitted. An example of that is a scientific number that I've written down here, where I've written 123.4 as equal to 1.234 E2, meaning I'd have to move the decimal point 2 positions across the 3 and across the 2 in order to represent the number correctly. And then we could also represent this as 1.234 times 10 to the second, as I just mentioned. And what we do is we always lead with one digit and then the decimal point. That's the custom. So you'll notice that I placed the decimal point here, not here, and not in some other point. Although that would be a valid expression by altering the exponent, we still don't do that customarily. One reason for that is it's often very difficult to see a decimal point out front, and then if we have to search for the decimal point, it makes it a little bit more prone to making an error. And so the customary place is to put it right after the first non-zero digit. And so that's how we'd represent a number. Now, to add and subtract such numbers, if we had a number like 3.1 e to the 5th, and we're going to multiply that by 2.0 e to the 9th, these numbers written out would be very large numbers because I'm going to have 9 more zeros after the 2, and I would have 4 more zeros after this 1. However, you'll notice that with this notation, I can take the 3.1 and multiply it by 2 and get 6.2. And you'll notice that, and we're going to cover this when we cover numerical uncertainty in a minute, I only have 2 significant digits here and here, so I need to restrict this to 2 significant digits. So this will be equal to 6.2. Now, what power of 10? We have 10 to the 5th power here times 10 to the 9th power here. So 10 to the 5th times 10 to the 9th will give us 10 to the 14th. So this would be e to the 14th. And therefore, we would have 13 more zeros going all the way across here. So you can see that scientific notation actually allows us to manipulate numbers more easily by moving the decimal point to this one position and then doing our addition, subtraction, multiplication, and division. And then, of course, what we would do is if we were doing multiplication and division, then it's very easy to handle the exponentials. But if we're doing addition and subtraction, it's a little bit trickier because we have to align the decimal point in order to do the addition and subtraction, as I'll show you right now. Our next point is numerical uncertainty. Numerical uncertainty follows from the fact that we never really measure anything in the real world to an infinite number of digits. First of all, we couldn't even write down the number of digits. There's no place in the universe to write an infinite number of digits down, even using every atom and every molecule in the entire universe, if it would stay in place and allow us to write or indicate with such a number. So therefore, something like the length of the room is going to be determined by the accuracy of our measuring devices, even using lasers and other extremely accurate devices. At some point, we enter the molecular and then the quantum domains, which means that the position of one wall is distant from another wall is just not known that accurately. And therefore, we have an uncertainty. We've indicated scientific uncertainty by saying we know this number 3.1 only to this accuracy and no more. Up here, that's not a decimal point there. In this 3.46, we know that we would imply here that we know that accuracy. And so it's difficult to write this, but in scientific notation, you can see by cutting off these zeros and maintaining the decimal position using the exponential, then it's obvious that we do not know these. If we did know those decimal places, let's say we knew 3 more decimal places, we would write it as 3.46000 e to the plus 8. And in that case, that says we know it's exactly this number of significant digits, that all of these digits have a meaning, and it is truly 000. But written like this, it is not. It implies you do not know any more digits that are significant. That means the digits that follow this 6 could be anything, except normally they would not round to a 7, so this would not be a 698 or something like that, but it could be a 3.4589 or something that would round to the 6 if we were unsure of those other digits. So there's just an uncertainty there associated with one unit. Likewise, when we looked at this number, we did put the 0 there, so you can see that this number is known to 2 significant digits. This number is known to 2 significant digits also. So consequently, when we multiply, if you multiply or divide, you want to retain the least number of significant digits in any of the things that you're using to multiply or divide. For example, if this were instead a 3.1 times 2 e to the 9th, then in fact, this digit here is only known to 1 significant digit, and if I multiplied these together, I would get 6.2 e to the 9th. But you'll notice that since this has 2 significant digits and this only has 1, then in fact I must throw away this significant digit and end up with a 6 e to the 9th. So in multiplication or division, I retain only the number of digits in the least accurate number that is being divided or multiplied. Why don't you do an example and see if you can work this. 3.25 times 1.1. What would that give us? If we worked that out, it would be 3.25 times 1.1. That would be 3.325, 5,753. And I believe I did that right. 325, 325, and then 5, 5, 6, 7, 5. We have 3 decimal places there, so the decimal point would go here. But you'll notice that if we left the number like this, it would imply that we know 4 significant digits, and that's not correct. Here we see that we only know 2 significant digits for the least accurate, so we must round this number to 2 significant digits, round the 7.5 off, so that this becomes 3.6, and leave it at that. And that would be our answer for multiplying these 2 numbers. Now, if we're adding or subtracting, rather than multiplying and dividing, we do things a little bit differently. Let's take these 2 numbers and now add them. And if we did, we'd have 3.25 plus 1.1. And when you do this, of course, when you add, you must line up the decimal points or decimal positions, or when you subtract. And if we did that, we would end up with 5, 3, 4. And you can see we have 3 significant digits here. But here we have an unknown digit right here. So we can't say that this is a 5. So what we have to do is we have to throw this away. If you wish, you could take that 5 and round it over here to a 4 and write that as 4.4. There are differing conventions on whether you round this or do not round it. Since we don't know what this is, it would be more accurate to say this could be any number, so it's probably more probable a 4.4. So I would leave this as a 4.4 rather than a 4.3, actually rounding that 5 off. Now, you'll notice, therefore, that if I add something, and now I'm going to take another example. Let's take a number 3,827.2, and I'm going to add to that number. Remember, this is unknown out here. I'm going to add to that number 0.003. And you'll notice that when I add these two numbers, 3027283, this implies that I know 3 significant digits. Well, it's not the number of digits altogether. Here we have 3 significant decimal places. And since we do not know what this decimal place and this decimal place are, these are totally unknown, we certainly don't know what the sums are here. Since this is unknown and this is unknown, we cannot know what these two are. And so, in fact, these round off, and by adding 0.003, we get the same number that we started with. Meaning that what we're adding, or if we were to subtract this, we get no further along, we get no different number than the number that we started with. So we're adding something that is down within the error of that particular number. Again, get your calculator and practice with these various scientific numbers. And remember that currently mathematics does not have a way of automatically keeping track of your error. And so what you got to do is, although the calculator will take this number here and multiply it or divide it by this number here, and you should try both multiplication and division, it does not tell you that it's 6.2 e to the 14th. In fact, it gives you a number that could be more accurate. It'll give you 6.200000000, and you have to know where that accuracy is in order to cut it off. In my personal opinion, we could say that we really don't have a good system currently for maintaining the accuracy automatically for digits and numbers when we perform arithmetic operations. It would really be great if we had a closed mathematical system based upon Boolean logic and a full-scale exacting arithmetic that would automatically maintain all of the exact positions and cut out those extra zeros as being worthless or meaningless. And worse than that, they're misleading because they imply that we know something that we really don't know. That currently does not exist. And in fact, the structure for that mathematically does not really close well. If you represent error by Gaussians and so forth, you find that they don't really close under all the operations of addition, subtraction, multiplication, and division. So in engineering, this is a very complex area, the area of numerical and logical uncertainty. In Chapter 2, we're going to begin with the kinematics of motion in one dimension. Basically, this is the motion of an object, a single mass that we can consider as defined by